Hello, my name is Mark Kuzyk from Washington State University, and today we're going to start Module 1 on the topic of scalars and vectors. So let's start by talking about scalars. Now, scalars are something very simple yet very profound, and basically it's just a number that represents the property of an object. So for example, here I have a ruler. The length of this ruler, which is about 18 inches, is a scalar. So it doesn't matter how I orient it or what direction I look at it, it still has that same length. And that's going to be a very, very important property. Because what this implies is that there is some inherent property that belongs to this thing. If that weren't the case, then physics wouldn't work, because what we do is we model things and we describe their properties. And if the properties are not of objects, then what does it mean to describe these objects? Now, secondly, here I have this book. And this book also has scalar properties associated with it. So for example, if I place the ruler against the book, we can measure the book's width. And so the width is a scalar property of this book. Now there's something more interesting here, because if this ruler was not a scalar and I went to measure this book, I wouldn't get the same answer necessarily every time if this ruler somehow depended on the orientation or how I looked at it. So now we can see the importance of a scalar property in the measurement device as well as in the object that we're measuring. Now secondly, we measured the width. We can now measure the height of this book. That is also a scalar. But it turns out that height times width, the product of two scalars, is also a scalar. So this book has some property of surface area of the front. Furthermore, we can measure its width. It's a very skinny book, and from that we can get the volume and so forth. So the important thing is that a scalar is something that's independent of how we're viewing it, of the coordinate system that we're using. Now let's move on to another example of a scalar, and that's temperature. So temperature is represented by a single number. In this room now, it is 68 degrees Fahrenheit. So that is a scalar. Now, a scalar can have more complex properties. So for example, here is a weather map. And we notice two properties of a weather map. First, it shows us a temperature at various places, like in various cities. And secondly, we need to know the time, because we know the temperature isn't constant over all times. So in this example, we can see that the temperature is a scalar, but it depends on position and it depends on time. So for example, if we look at Minot, North Dakota, it happens to be 36 degrees on October 28th, 2014 at 1:20 p.m. Eastern Time. So the place is North Dakota and the town of Minot, and we need to know the time. The temperature is a scalar because the measurement is independent of the angle of the thermometer relative to the ground, for example, or it's independent of the coordinate system that we pick to locate the city where the temperature is being measured. The coordinate system can be centered in the middle of nowhere in Wyoming, or the coordinate system can be rotated to a funny angle and centered in the middle of the state of Idaho. Independent of how we set up the coordinate system, we will get the same temperature. Also, we can refer to the coordinate of the city by longitude or latitude, or by its location given the name of the city. So the thing we see here now is that a scalar can depend on other properties. And so it can be more complex than just a single number that's immutable. But the important thing is that when we give you the temperature of a particular place and a particular time, it is an immutable property of that place at that time. Now let's go back to the example of the ruler. The ruler, if we place it into an oven, it will expand when it gets hot. And if we place it in a refrigerator, it'll contract. So we can see that even the ruler is not something that is a constant as a function of temperature. So one scalar can depend on the properties of another scalar. So when we're doing a measurement, for example, when we're measuring this book again, we need to take into account the fact that the ruler can shrink or expand and the book can shrink or expand depending on the temperature. So we have to be very specific to describe the temperature at which the measurement was made, for example, and then take into account this expansion and contraction. So there are other issues that need to be considered. Okay, so as an assignment now, I'd like you to go out and look at things around you. So go for a walk outside and think about things that are scalars and vectors. So for example, as a hint, here we have this book again. This book has words in it. So the number of words is a scalar. The number of characters is a scalar. The weight or the mass of the book is a scalar. So go around and look at various items and then think about which things might be scalars and why or why not. Now finally, as I mentioned to you in the introduction, sometimes we lie to you. And it's not on purpose, but we're lying because things are more complicated than we let on. So for example, if I have an observer that's traveling close to the speed of light and looks at this book, they will see that the book has contracted in the direction of motion. Now it turns out that in everyday life, this effect is very, very tiny, and so you'll never notice it. So for all practical purposes, this length of the book is a scalar. But secondly, it turns out there is a scalar property associated with this book when you're looking at relativistic effects, and that's called its proper length. So if you do the measurement at rest with the book, you will always get the same length. Now it turns out that if we are in a gravitational field and we move the book up and down relative to, let's say, sea level at the Earth's surface, the width of the book will change. Also, as we rotate the book around like this, its length here will change. And so those are due to gravitational effects. So even though we've defined these scalar quantities, we have to be careful that when we go into new regimes, like at high speeds or strong gravitational fields, that we need to take those things into account. But when it comes to gravitational effects, you need to be near the surface of a neutron star or a black hole in order to see a large effect. So for all practical purposes, these effects aren't there. And on the topic of this book on size, it turns out that when you go to very, very, very small size scales, very interesting things happen. So if you take this ruler, let's say, and you cut it in half, the two lengths of the two pieces will not add up to the length of the ruler. So really funny things happen on small scales. So I mention these other things not to confuse you, but to basically whet your appetite so that you hang in there with physics and study it so that someday you can get to the point where you can understand these very, very interesting topics. Thanks, and go out there and look for scalars.